Good day, everyone. We are discussing on the chapter 29 with the topic electromagnetic induction. So this is a important concept in physics that explains how the electricity and magnetism are closely related. So this is essential or important because it forms the basis of many modern technologies that we have, like the generators, transformers, and electric motors. We do have the learning goals that we are looking forward in this discussion. So we aim to understand Faraday's law, the determining the direction of induced EMF, explain how a changing magnetic flux generates an electric field, and even recognize the importance of the Maxwell equations and superconductivity. So next slide is what is electromagnetic induction? So it refers to the process where changing magnetic field induces a electric current in a conductor. So this phenomenon was discovered by Michael Faraday in 1830s. So the key idea here is that electricity is not produced by magnetism alone, but by a change in the magnetic environment. Next slide is the induction experiment. So in this experiment, scientists observe that when a current in one coil changes, a current is induced in a nearby coil. So this induced current exists only while the magnetic field is changing. So from this observations, we define induced current as the current produced and induced is the current produced and induced EMF as the voltage that causes it. So this shows that motion or variation is essential for induction to occur. Next slide is the coil and the magnetic field. So this slide shows that that coil placed in a constant magnetic field does not produce a current. However, a current is induced if there is a change in the environment or there is a change in the strength of the magnetic field. So the orientation, the area, or the position of the coil. So this highlights that induction depends on changes, not static conditions. Next slide is the magnetic flux. So, magnetic flux measures how much magnetic field passes through a surface. So it depends on the magnetic field strength, the area, and the orientation of the surface. So when the surface is face on, the flux is maximum. And when it is edge on, the flux becomes zero. So learning the magnetic flux is important because changes in flux directly lead to induced electromotive force or EMF. Next slide is the Faraday's law of induction. So Faraday's law states that an EMF is induced when the magnetic flux through a loop changes over time. So the magnitude of the induced EMF is proportional to the rate of change of magnetic flux. So this law explains how electrical energy can be generated from mechanical motion, which is the principle behind power plants. Next is the direction of induced EMF. So in this part, focus on determining the direction of the induced EMF. So the direction depends of whether the magnetic flux is increasing or decreasing. So, using the right hand rules and field direction diagrams help us visualize the direction of the induced current, which is crucial in circuit design and electromagnetic devices. Next slide is the Faraday's law of for a coil. So this part is when a coil has multiple turns, the induced EMF becomes larger. This is why generators use many loops of wire. And the total EMF is equal to the EMF per loop multiplied by the number of turns. So this principle increases efficiency in electrical machines. And next is the Lenz law. So the Lenz law states that the direction of the induced current is such that it opposes the change that causes it. So this law is a direct consequence of the conservation of energy. So it explains why induced current often resists motion, such as in braking, magnetic braking systems. Next slide is the emotional EMF. So emotional EMF occurs when a conductor moves through a magnetic field. So the motion causes charges in the conductor to experience a magnetic force creating a voltage. So this is another way EMF can be induced without changing the magnetic field itself. Next slide is the induced electric field. So a changing magnetic field can create a circulating electric field even without the conductor present. So this shows that electric fields do not always come from charges. So this concept depends our understanding of how electric and magnetic fields interact dynamically. The next is the eddy currents. So eddy currents are loops of induced current formed in bulk conductors. While they can cause energy loss, they are also useful in applications such as metal detectors and magnetic braking. So this demonstrates both the advantages and disadvantages of electromagnetic induction. Next slide is the displacement current, which focus in the Ampere's law alone cannot it states that Ampere's law alone cannot explain the magnetic field during the charging of a capacitor. So this Maxwell introduced the concept of displacement current, which accounts for changing electric fields. So this idea completed the symmetry of electromagnetic theory. Next slide is the Maxwell equations. So Maxwell four equations summarize all known relationship between electrical and magnetic fields. So they show that changing electric fields produce magnetic fields and vice versa. So these equations unified electricity and magnetism into a single theory called the electromagnetism. Next is the superconductivity and Meissner effect. So superconductors lose all electrical resistance below critical temperature. So the Meissner effect occurs when a superconductor expels magnetic fields from its interior. So this makes superconductors perfect diamagnets and allows phenomena such as magnetic levitation. So, in conclusion, electromagnetic induction explains how changing magnetic fields generate electric currents. So, through Faraday's law, Lenz's law, and Maxwell's equation, we see how electricity and magnetism are deeply related or connected. So, these principles are essential to modern technology and continue to shape the modern advancements in science and engineering. That's all. Thank you.